Okay, so let's get started. So this is the problem from your worksheet worksheet 8. This is problem number 4. Like I said before, it's a little bit tricky, so I want to show you how to do this. So basically, you can model your leg as some kind of cylindrical thing. Okay, so that's a part of your leg, and it says we are considering the length of 40 centimeters between knee and hip. So that's the 40 centimeter length, and the diameter is 12 centimeter. So this diameter is 12 centimeters, and then you are applying the potential difference of 0.75 volts. That causes the, so between any 2 points, okay, you apply potential difference of 0.75 volts. That causes the current through that, current of 1.6 milliamperes. So it's not very clear where the potential difference is being applied. So it could be here and here between the 2 points. Okay, so it's asking, so there is muscles muscle and fat in the leg. So it's asking what are the fractions of muscle and fat in the leg. Okay. So it's asking for fractions, so we want to know just the fraction, not the actual amount, actual volume or actual mass. It's just the fraction. So let's say F sub F is the fraction of fat, and F sub M is the fraction of muscle. So fraction and fraction should add up to 1. Okay. For example, if you have 1/3 of fat and 2/3 of muscle, that should add up to 1. Okay, just adding fraction gives you total to be 1. So total of that is 1. So we can write this as fraction of muscle is 1 minus fraction of fat. So we need to find Fm and Ff. So we can find the cross section area. So the cross section area of the leg A, let's call it A, total cross section area is pi r squared, or in terms of d you can write pi d over 2 squared. That's the area. Pi 3.14, and d is diameter. Diameter is given, so 12 times 10 to negative 2 over 2 squared. Can you guys do the calculation? I didn't bring my calculator here, so let's see. So I can cancel this and this for 6. If I do the wrong calculation, please let me know. 3.14 times 6 times 10 to negative 2 squared. So that gives me 1.13 times 10 to negative 3 meters squared. Okay. So that's the total area, and part of that area is fat and part is muscle. So the area of fat would be that times the fraction. Okay. So 1.13 times 10 to negative 3 meters squared, that's the total area. If you multiply that by fraction of fat, that will give you the area of the fat, and area of muscle is total area times the fraction of the muscle, which is F sub m. Okay. Now we can, with that we can find the resistance offered by each of the component. So resistance offered by fat, we can find that. Resistance offered by muscle, we can find that. So resistance is given by rho, resistivity of fat, length of the fat over area of the fat, and Rm is resistivity times L over area of muscle. I am using the same length because the length is same throughout the leg. Okay, so length is same. What is different is the area. Throughout this length there is both muscle and fat, only the area is different. Now this rho f and rho m are not given, so we need to do Google the value of these things. So this one would be 25 ohm meter, so that's the unit for resistivity. Okay. And this one is 13 ohm meter. Okay. So with that, now let's find the expressions for Rf and Rm. So this is 25. Resistivity of fat is 25 ohm meter. Okay, so length, what is the length? 40 centimeters. 40 centimeters, 10 to negative 2 meter. Okay, that's the length, and the area, we already found the area. Area of the fat is 1.13 times 10 to negative 3 meters squared times F sub f. Okay. Likewise, we can find the expression for resistance offered by muscle. So rho of muscle is 13 ohm meter, length is 40 centimeters, that's the length, and the area is area of muscle is 1.13 times 10 to minus 3 meters squared, and that's Fm. Okay. So resistance is that. I can do the calculation and then simplify that. So that would give me, let's see, 25 times 40 times 10 to negative 2 that divided by that gives me 8.846 over Fm. Okay, so that's Rf. So you can do the calculation. I may be wrong, so if you don't see the same answer, please let me know. There is times 10 to 2 also. So for this one, 13 times 40 times 10 to minus 2 over 1.13 times 10 to negative 2. So that gives me 4.601 times 10 to 2 over Fm. This one is not Fm, this is Ff, okay, fraction of the fat. So this one, that's F sub F. Okay, so all I did here is found the area of the muscle in the leg and area of the fat in the leg, and then I'm finding the resistance offered by the fat content and the muscle content in the leg. Okay, so again we have here fat and muscle in the leg, and they are offering some resistance to the current that we are applying. And all these things that we are doing so far is to find this Fm and Ff. Okay, our purpose here is to find F sub F and F sub M. That's what we want to find. Now, the clue here is we are given delta V and we are given total I. Okay, and we know we can relate these things. These are given. We can relate these things to resistance. Okay, so these are all related by Ohm's law. So Ohm's law gives us delta V is equal to I times R. So we can find I that flows to the fat, that's given by delta V over R, and we can find the current that flows to the muscle, that is given by delta V over resistance of the muscle. Okay, so delta V is, we applied 0.7 volts. Okay, is that what the voltage is? So let's see, 0.7 volts, yes. And then RF is what we found, 8.846 times 10 to 2, and then this FF, okay, it's here, F sub F, that's the current passing through the fat, current passing through muscle, 0.75 volts over resistance of the muscle, 4.601 times 10 to 2 over Fm. So let's do the calculation, simplify that. So this gives me 0.75 divided by 8.846 times 10 to 2 . So that's 8.47 times 10 to negative 4, and this F sub F goes on the top. Okay, this goes top here, numerator, f sub f. Likewise Im, so 0.75 divided by 4.601 times 10 to 2. So that gives me 1.63 times 10 to negative 3, and this one goes on the top, so f sub m. Again, if I have a wrong number, please let me know. So this is the current flowing to the fat and current flowing to the muscle, and when you apply this delta V, you get the total current of I is given in the question. So you are getting total current of 1.6 milliamperes. Okay, so 1.6 milliamperes is the total current that passes through both fat and muscle. That means our total current is I, and part of that flows through fat and part flows to the muscle. So it's the total current is the sum of current flowing through fat and current flowing through muscle. Okay, so total current 1.6 milliamps, milli is 10 to negative 3. IF (8.47) times 10 to negative 4 FF plus 1.6 times 10 to negative 3 FM. So just to simplify, we can divide both sides by 10 to negative 3, okay, just to make the terms simpler. So then this and this will cancel, this and this will cancel, this and one of the 3's will cancel, so we'll have 1.6 amperes. Now F sub F and F sub M are related, so we can express one in terms of other. So we know F sub F plus F sub M is 1, so we can write F sub F is 1 minus F sub M. Okay, this will help us to write this in single variable. So this one is 8.47 times 10 to negative 1. So F sub F is 1 minus F sub M. Okay, so that plus 1.63 FM, and then 1.6 is equal to 8.47 times 10 to negative 1. So multiplying this to that and then that to that, we get minus 8.47 times 10 to negative 1 FM, and then plus that 1.63 FM. So then you subtract this from that, so you take this to the left and then subtract from 1.6. What you get is, let's see, so if you do the subtraction, you get 0.753, and then these two have the same FM, so you can do minus 847 times 10 to minus 1, and that is plus 1.63. You take FM out because it's common, and then subtract this from that, so 1.63 minus 8.47 times 10 to minus 1, and that gives me 0.783 FM. And then, so on the left we have 0.753. So FM then would be, taking this to the denominator here, 0.753 over 0.783. So that will give me 0.753 over 0.783. That's 9.96. And then to find F sub F, that would be 1 minus FM. That means 1 minus 0.96. So that would be 0.03 0.03 something, okay, 0.0. So this is 0.962, that's what I got. So that would be 0.038. So the fraction of fat is that means 96. So if you convert this to percent, so it would be 96.2% of the leg is muscle, and then this converting to percent would be 33.8% of the leg is fat. Okay, so that's what you need to find. Let's see number 5. So it's asking for power. So number 5, an electric eel develops a potential difference of 450 volts, driving a current of 0.8 amperes for 1 millisecond pulse. For this pulse, find the power, total energy, and total charge that flows. So in order to solve this problem, we need to know how to find the power and how to find the energy. And we know from introductory physics, how do you define power? You guys remember? Power is, that's right, but I'm asking what you learned about power in introductory physics. So that's something that we will talk right now, but what you learned about power in like physics 1. Force times distance is work. It is related to power, but it's not power. So that's work, but it's related, okay? So work is also change in energy. So power is change in energy per unit time, or work per unit time, how much work you do in a second of time, okay? So work done per unit time, that's the power. Or you can say power is energy delivered per unit time. How much energy you can deliver per unit time, that's the energy, that's the power. So power, you guys may know, unit for power is watt. Okay, watts, or capital W. And this is the mechanical power, and electric power is given by current times voltage, okay, I times V. So you can use either this one, energy per unit time, as the power, or you can use power is equal to I times V. Okay, so you have two formulas here. Now in the problem, let's look at the problem. So you can model the eel as some kind of resistor, some kind of substance with some resistance. Okay, and the potential difference across the eel is 450 volts, and when the potential is that, it can send the pulse. Okay, pulse is one single wave of electricity. It can send the pulse that has the current, so it sends the pulse that has the electric current of 0.8 amperes. So the current flowing through the eel's body is 0.8 amperes. So what's the power of the current produced by eel? Okay, so we want to find power. So power comes from current and voltage. So power is current times potential difference. I should write here delta V. So sometimes instead of writing delta V, people only write V. Okay, if you see V, that means it's delta V. So I times delta V. I is current 0.8 amperes, and delta V is 450 volts. Okay, so that will give you the power in watts. And then what's the total energy delivered by the eel during that time, 1 millisecond. So it's producing the pulse for 1 millisecond. During that time, what's the energy delivered? So we have this formula. Power is energy over time. Okay, so energy delivered during some time, certain time, is power times time. Power is, we just found from here, and that times 1 millisecond, 1 times 10 to negative 3 second. Okay, that gives us the energy. Energy is measured in joules, right? Capital J. And then for the third one, what's the total charge? Total charge. We know the definition of current. Current is charge times time. Okay, we want to find the total charge. So total charge would be I times T. I is current. Current is 1 millisecond. Milliampere, sorry. Let's see. Now current is, sorry, that's the time. Current is 0.8 amperes, but the time is 1 millisecond. So current times time gives you the total charge. Okay. Now this formula is true for any kind of electric component. So for example, if you have a light bulb or some kind of other electronic component, let's say you have a light bulb or some kind of electronic component, let's say some component that has resistance of 10 ohms, and you are applying potential difference using a battery. So this is a battery with 1.5 volts. So what's the power in this circuit? What's the power of the resistor? Okay. We want to find the power of this one. So how to find power? We know power is I times delta V. Okay. So we don't know I in this circuit, and we don't know V. So how do we find the power? Any idea? We know that we can find I. Okay, we can find I because we have Ohm's law. Ohm's law gives us I. Delta V is I times R. So I would be delta V over R. So delta V is 1.5 volt over 10 ohms. So that would be the current through the wire. So that's 0.15 amperes. So there is 0.15 amperes of current in this circuit, but we don't know what's the potential difference here. This is the potential difference of the battery, but we don't know the potential difference here. If it is parallel, this would be same. Okay, potential difference will be same, but let's say we don't know it, then how do we find? So I is known, and delta V, we know from Ohm's law, delta V is I times R. So I times R. I and I is I squared, current through the resistor or through the circuit, and R. Okay. So now we know I squared is 0.15 amperes squared, and R is the resistance 10 ohm. Okay. You do that, that will give you the power. So sometimes you can write the formula for power in other ways. Okay, like you can write power as I squared R, or you can also write power as in terms of delta V. You can write delta V delta V square over R, or it's also P is equal to I times V. So these are all different expressions for power. So you can change this formula by using Ohm's law into these forms, but they are all same. Okay. Okay, so let's look at this question, and I want you guys to think about this question. Let's look at both of these questions. Okay, so let's look at the first one. The charge flowing through a light bulb attached to 12 volt battery. We have a light bulb connected to a battery. in 14 seconds that much charge flows through this. Okay. So Q is 30 coulombs for time is equal to 14 seconds, and delta V is 12 volts. What's the power delivered by, or what's the total energy delivered by this bulb during that time? So we want to find energy delivered. So we know relationship between energy and power. So power is energy over time. So if we could find power, then we can find energy. Okay. So first we need to find the power to find energy. So what's the formula for power? I times V, or I times delta V. I is, how do we find I? Yeah, Q over T. Charge over time, charge is 30 coulombs, time is 14 seconds. That gives us current, and delta V, or V, is 12 volts. Okay, that gives us power. And once we have power, we can find energy. Energy is power times time. Power is, we found that, and then time is during 14 seconds. So let's find the number here. I have 30 over 14. That gives me 2.14 amperes. Okay, and 2.14 amperes times 12. That gives me 2.57 watt. Okay, and then 2.57 watt times the time gives me the energy. 360. Huh? Is that 25? Oh yeah, 25. Sorry. I don't know why. Maybe my calculator has scientific format, so I forgot the 25 watt. 20. Yeah. Not exactly 25, but 12 times 2.14. Yeah, 25.68. And then you get the answer. So that's about 360 joules. Okay. So that's that. And then just a minute to do this last one. It shouldn't take more than a minute. We are almost out of time, but so this one is pretty straightforward. Okay. The power rating is given, P is given 400, so 0.8 watt, and then resistance is given, R is 400 ohms, and it's asking what's the current. Okay, current is what? So we can write power is equal to I squared over I squared times R. This is another way to write power. It's the same thing as I times V, and then I is what we need to find. So I would be P over R square root. Okay, so square root of 0.8 watt, and the resistance is 400 ohms. And that will give you the current. Which is 4.47 times 10 to negative 2 amperes. Okay, I think we are out of time, so that's all for today. Have a great weekend. If you have any question, I can answer your question. If not, then if you guys have any question about homework or worksheet, please let me know. You can email me, or you can come to my office during my office hour, either today or Monday.